So the first observation is that treating this as two separate problems, a problem where I have to build partial product circuitry and a problem where I have to build adder circuitry, we might be able to get a better insight about what building block, and so that seems to require at least a couple building blocks. What I'm going to do is suggest that, look, it looks like we have a full adder for about every partial product. Maybe we should combine the two. Maybe we should make a building block that actually thinks about everything that needs to be done and building a building block that goes from the operands to the answer sort of as quickly as we can. Okay, so instead of building circuitry that does the partial product, creates the partial products, and circuitry that does the addition, we're going to build a building block that sort of does a little bit of both and then wire them up in a way that causes us to solve the multiplication problem correctly. So we're going to build a single building block, one of these building blocks here, which is a combination partial product generator and also deals with the addition in the columns as we go down, right? So think of this building block as taking in 2 bits from the columns above. So the two bits of whatever the sum is. It has a carry in and a carry out from carry in from the columns to the right, and it will produce a carry out to the columns at the left, and it will produce some bits out, right? So in general, what I'm going to do is multiply A times B to come up with a 2-bit result. I'm going to add it to those bits of the partial product coming down from the top, and with a carry in from any carry outs of previous things to my right, operations in bits with less significance, arithmetic significance, and I'm going to produce a 2-bit sum and a carry out. So here's a design. So notice that we basically have the 2 operands sort of coming in diagonally, and then the carry in from the bits of lesser significance, the carry out to the bits of more significance, and then the 2 bits from above and the 2 bits below. And here's a little piece of circuitry involving the full adder building block. It adds together 2 bits and a carry in, so 3 incoming bits, and produces a sum and a carry out. Okay, so this is our little building block, like so. So this is really the only thing where you actually have to do circuit design. And now we're just going to figure out how to sort of piece these building blocks together to form the actual resulting multiplier. This is not the most efficient thing. Here I have a full adder who has a constant input. And you say, well, couldn't I redesign that? I don't need quite as many gates as every gate in a full adder, because in some sense I'm only adding together 2 bits. And the answer is sure. There's lots of little optimizations here, which you may have fun doing. But we're really just trying to get to the larger point about how the structure of the problem can be exploited to achieve certain ends, which I'm about to get to. Okay, so now we get to the question about latency. And you might say, well, there's n additions, and it takes, so I have to add together order n different partial products, and each one has about order n bits in it. So maybe if I go off and imagine how long it's going to take to do this, it might take order n squared. And we can sort of say, well, so look, it's I have n bits vertically, n additions to do, and then I have n bits across. Okay, and so that would suggest that maybe it's n times n is how long I have to wait. But if you think a little bit about how this works, you can see that the actual propagation of information always is down and to the left. So some bits are going down and carry bits are going to the left. It turns out the longest path you can find through this circuit, if you sort of look bit by bit by bit, is every time you take a step, and it doesn't matter which path you follow, the carry path or the sum path or some mixture of the carry and sum paths, you're either moving to the left by 1 or you're moving down by 1 as you exit the block. Right? And you can only move left n different times before you get to the end of the arithmetic problem, and you can only move down about n times before you run out of things to add together. And so it means that the total path is somewhere around 2n. It's not n squared. Does that make sense? Do you sort of see why this is your insight, right? Which was that somewhere around order n is a much better estimate of the actual latency here. Okay, and the answer is, another way to look at that is to you know, what happens is that, well, I won't try to confuse the issue any further. Is that, everybody sort of happy with sort of the order n as the latency of this circuit? Okay. Okay, so this brings us to, okay, a slightly more accurate picture. If we're going to use this hardware structure, now we've been pretty specific, it still takes about n squared pieces of hardware. The hardware cost is about n squared because I have n squared building blocks, right? N squared of each of these little guys. And then each guy has constant cost. You know, has one full adder, you know, or two full adders and an AND gate. So the hardware cost for each block is constant, and I have about n squared blocks. So the hardware is n squared. The latency we just saw on the previous slide talked about it being order n. And the throughput, because this is a combinational circuit, is 1 over the latency, or 1 over n. We produce one answer every n time units. So this was, you know, a long way around the barn to get to maybe a result that it wasn't too surprising to you. But I wanted to set up this structure because now, in quick order, we're going to be able to do some pretty interesting things with this structure that will allow us to put up remarkably different stickers here, our little EPA stickers about costs and mileage and throughput and latency. We're going to be able to redesign our circuit using some interesting observations that we're going to spend the rest of the lecture making. Okay, and you know, this was a pretty naive implementation. There are lots of tricks you can do, which you can learn about in other courses, that sort of make the hardware twice as small. So we're sort of, that doesn't change the order of the cost of the hardware, but it does reduce some of the constants and makes a big difference.